It's my pleasure to introduce Daniel Glaser, and he is a senior researcher at the CSIR manufacturing facility in South Africa. He has written numerous papers on laser shock peening and the residual stress introduction by that process. I look forward to hearing what you have to say and some of the work that's going on down in South Africa. So with that, Daniel, the floor is yours.
Thank you very much, David. Hello, ladies and gentlemen. First of all, I'd like to thank the organizers for hosting this event. I would also like to acknowledge the co-authors who have played a crucial role in the work that is going to be presented. So the title of this talk is New Frontiers for Industrial Laser Shock Processing in South Africa. So just to not take any chances and prevent any potential bandwidth issues, I'm just going to turn off my video. Okay, so this is just an overview of this brief talk. I will give an introduction to my institution and then an overview of the laser shock peening facilities in Africa. There are 3 industrial applications that will be discussed. The applications are for life enhancement for our local power generation and mining sector, as well as distortion correction for an application in the aerospace sector. Finally, we'll give a brief outlook and there will also be some time to answer some questions, but please feel free to post questions in the Zoom chat. As mentioned by David, I work at the Council for Scientific and Industrial Research in South Africa, which is our national science council. Within the CSIR, the National Laser Centre is part of the manufacturing cluster, and our division is called Laser-Enabled Manufacturing. The technologies that we work on are shown here, and this includes laser cutting, laser welding, cladding, hardening, micromachining, laser additive manufacturing, and of course, laser shock peening. Some of these technologies are already offered as fully commercial services, but we're still very much in the R&D phase for additive manufacturing and LSP. Our center's flagship project is the additive manufacturing machine called Aerospace, and this is one of the largest and fastest powder bed machines in the world, as it has a 5 kilowatt laser system and a build platform of 2 meters by 0.6 by 0.6 meters. So the objective of this machine is to build components for the aerospace industry, such as landing gear from titanium. I'm also a research associate at Nelson Mandela University, where the mechanical engineering department has a consultancy division called eNtsa, who specialize in bespoke engineering solutions for industry. Some of the key technologies developed are shown here. On the top left, you can see there's a friction stir welding for a large aluminium road tanker, where the team is standing in front of an 8-meter long weld. In the petrochemical and power generation sectors, structural integrity is of great importance, so a number of sampling technologies have been developed to enable remaining life to be determined. Nelson Mandela University are also well known for new innovations already used in industry, where their weld core process has been developed to enable deep core samples to be extracted from pipes and then repaired using friction hydropillar processing. The weld core process has also been applied to turbines in power generation. And in terms of peening, a very exciting new type of peening called whip peening has also been developed by Nelson Mandela University. And this was to address residual stresses after grinding of cracks from turbine steeples and has already been implemented in industry. Okay, so for laser shock peening, our facility is based at the CSIR National Laser Centre. Some of you in the community may have been fortunate to have visited our labs in 2016 at the 6th International Conference on Laser Peening. At this time, we only had one laser system, which was operated at 1064 nanometers. This system is widely accessible to students through what we call the Laser Rental Pool Program, and we get a lot of work from Professor Glaser at the University of the Witwatersrand. We now also have a second system, and this is more dedicated for industrial projects, and this can operate at 532 or 1064 nanometers. We've also added a laboratory XRD instrument for quantification of residual stresses. So while this presents our current facilities, we are also considering making our infrastructure mobile to address some of the local industrial requirements. And within the broader CSIR, we have a number of metallurgical facilities, as well as a certified mechanical testing facility. Across the country, there's also other highly relevant infrastructure that we access on a regular basis, along with our collaborators and partners. eNtsa is a research nuclear reactor with a neutron diffraction strain scanner, and South Africa is also a member of the European Synchrotron Research Facility. Professor Palese, based at the University of the Witwatersrand, has an incremental hole drilling instrument, which we access regularly. And Nelson Mandela University also have incremental hole drilling, as well as an XRD device to complement our national capabilities. Although laser peening is advancing rapidly, in terms of commercial work, the technology can primarily be categorized as high energy LSP and low energy LSP. The high energy approach is used commercially by companies in the United States, working mostly at infrared wavelengths, and typically use a thin water layer. Typical energies can be on the order of 10 joules per laser pulse. Where on the other end of the spectrum, we see that the lower energy approach has been developed in Japan to operate at 532 nanometers and works without a protective coating, where the energy levels are typically less than 0.2 joules per laser pulse. In South Africa, we are operating somewhere in between that, so what we classify as the mid-range energy LSP process, with pulse energies approximately 1 joule per pulse. So depending on the application, we may choose to use a coating or work in the direct ablation mode at either 1064 or 532 nanometers. Okay, so regarding our industrial applications, one of the primary projects is something that we're developing for steam turbine blades for Eskom, who is South Africa's power generation utility. In fact, Eskom provide 40% of electricity in Africa. So for steam turbines, low pressure blades have a mass of over 20 kilograms, and these spin at over 3000 RPM and operate in a wet steam environment. The highly stressed blade attachment routes are typically susceptible to failure mechanisms such as fatigue and stress corrosion cracking. These components are already conventionally shot peened, and this is somewhat standard practice globally. Unfortunately, a catastrophic failure of one of these blades has already occurred, and this results in damages with a cost of over 100 million euros. This has actually raised concerns about the suitability of the shot peening process for three-dimensionally complex sections. So the blade shown here has an attachment referred to as a fir tree due to its shape. And the graph shows the typical benefit from the conventional shot peening process by introduction of a compressive residual stress to a depth of about 0.2 millimeters, where a corrosion pit may actually have a similar dimension. So the process development for this project started with optimization of process parameters for the laser system and material combination. We have conducted detailed studies to ensure that we can produce the desired effect, as seen by the graph on the top left. And this gives an example of being able to control both the depth and magnitude of compressive residual stresses for different process combinations. Our XRD instrument has been quite useful to study detailed features on the surface and enable a comprehensive understanding of resulting effects, as you can see on the bottom left with stress surface maps. Optimization parameters enable deeper level, the optimized parameters enable deeper levels of compression than conventional mechanical shot peening as expected, seen by the graph in the center. Combining these two, the LSP process has also been shown to produce lower surface roughness than the mechanical shot peening process. In combining the deeper levels of compression with improved surface roughness can result in superior performance. For example, we have conducted simple three-point bending tests with multiple samples of the base material that only failed at a few 100,000 cycles. However, all laser peen samples actually reached over 5 million cycles and actually haven't failed, which is where we defined run out. In addition, initial U-bend stress corrosion cracking samples have also indicated promising results without failure of LSP over the defined testing period. Parameter development has primarily been performed on simple flat samples. So for the actual application, the geometry of the blade attachment region is a significant challenge. Development has therefore also included different geometries, and the image here shows strain maps obtained using a technique called Bragg edge neutron transmission, and this work has been performed in collaboration with Professor Michael Fitzpatrick at Coventry University. A simple groove can be shown to achieve a uniform level of compression, and this technique has also been used to evaluate the LSP process applied to a full-scale 2D slice of the blade attachment root. The results for the first iteration are shown on the top right, where compressive strains are shown in blue. For this project, the current status is that we are busy with the development of a prototype machine, and this will enable implementation of the mid-range laser peening process. Recently, we have also started projects with our local mining sector for life enhancement solutions. The current projects are for a particular type of mining operation known as raised bore drilling. The schematic on the left shows how the first step of the process is to drill a pilot hole for a shaft, and this is attached to a hydraulic boring machine on the surface. A large reamer bit is then attached to the shaft, and the reamer has cutting heads, and this is rotated and raised to break the rock. The rock then falls into a pile in the mine shaft, which can then be collected later. So due to variability of rock mechanics, highly variable loading can occur during drilling, and the load-bearing components are exposed to a harsh environment, which makes them susceptible to stress corrosion cracking as well as fatigue. In addition, drilling companies are pushing the limits by drilling larger diameter holes to greater depth. In fact, a number of catastrophic failures have already occurred, and these have costly downtime consequences. Therefore, an advanced life enhancement solution for critical load-bearing components, such as using laser peening, is highly desirable. So the material of interest for this application is a fine-grained medium carbon chromium nickel molybdenum alloy steel. So this is AISR 4330V. And this is quite a common material in the mining industry due to its excellent hardenability, but also an excellent combination of high strength with exceptional impact properties. So while we are still busy on the parameter optimization for this project and this material, we already have some promising proof of concept results from simple 3-point bending fatigue testing. I must state, though, that to address the mining industry, or at least the local mining industry, a major challenge to this work is that LSP is still somewhat of an expensive technology compared to alternatives. We therefore still require further process parameter optimization to decrease processing times. We also have to start developing capabilities to implement the process on full-scale 3D components, as the dimensions of these components are often in the range of meters, with mass often in the range of tons. So we have a strong focus on our future capabilities to address large-scale components. While the mining and power generation projects required life enhancement solutions, our aerospace project has been concerned with the less common use of laser peening technology to implement precision engineered distortion of thin components. Our partner for this work was Denel Aerostructures, who fall within the Denel Group, where Denel is actually Africa's largest defense equipment manufacturer. And they manufacture a large number of precision components from machined aluminium. And as we heard from some of the previous talks, precision components machined from aluminium can occasionally distort. This is usually in response to residual stresses within the billet, which have been removed. Due to the tight tolerances in the aerospace industry, a small geometric deviation from the required geometry requires the component to actually be scrapped. So the purpose of this project was to develop the laser peening process as a distortion correction tool for machined aluminium components. So the photograph on the right shows the intended CAD geometry of the actual component provided. And at the top, you can see the actual measured geometry indicating the resultant distortion. So we won't have time to go into all of the details of the process development, but I'm very glad to say that we were able to correct the distortion by applying the laser peening process to different sections of the component. And the contour maps on the right just give a visual indication of the distortion after machining, as well as the LSP distortion correction. The before and after results for LSP is also shown graphically in the center. So the objective here was not to achieve life enhancement. However, very careful consideration was still required to prove that the structural integrity was not compromised. So although the aerospace component processing has been successful to achieve the objectives, the component isn't in service on an aircraft yet. However, we have subsequently used the knowledge gained from this work to apply the process for another application, and this is for 15mm thick aluminum alloy 7075 components. We were provided 4 components by a manufacturer in South Africa, each with a different level of distortion, and we were given a 2-week window to offer a solution. We were able to correct each component successfully, and these are now in service. So this was a major milestone for the South African laser peening group, as it represents the first components that have been laser processed to actually be used by local industry. So just as an outlook moving forward for the future, although we still have a long way to go to realize the benefits offered by laser peening technology in South Africa, we certainly have a number of exciting projects with local entities. As a future outlook, the South African Laser Peening Group will most likely be using the mid-range energy LSP process. And as we continue to push forward, we actually see that development of advanced manufacturing solutions certainly comes with a number of challenges. So firstly, at least in South Africa, industry requires the value from the laser peening solution, and they are really not interested in the development of the capabilities to get to that solution. So we therefore find ourselves in a innovation chasm in South Africa, where we need the full capability to be established first before a solution can actually be offered, at least on a commercial basis. So this leads to the next challenge, which is of course funding. So we usually have extremely limited resources as well as budgets, and we're often stretched to the max. So we often try to address this through collaborations. So while we have a number of challenges ahead of us, we actually have a number of exciting opportunities as well, and we look forward to bringing the value of laser peening to the South African market. So the work presented here would of course not have been possible without key collaborations listed, as well as funding from various agencies. And yes, hopefully we can get to some good questions.
Thank you, Daniel. Appreciate your presentation. I have a question, and I will wait for a minute or two to see if anybody else has a question. You talked about the one application of straightening some of the aerospace components. Do you have a vision for what maybe the next component that might be in production on a more routine basis?
In terms of that project in South Africa,
yes,
that particular component was actually provided by the company, as historically it had actually given a lot of problems with distortion in the past. The company were actually interested in using laser peening for a new project that they were going to launch, where they would be a manufacturer of a particular aircraft, and they wanted to look at technologies in the future to try and address potential problems coming forward. Unfortunately, at this stage, it looks like that project with that manufacturer won't move forward, which was a great disappointment for us. But we've certainly learned a lot from the process and would be very keen to move forward with any other potential interested parties.
Okay. Don't see any other questions at the moment, and we are out of time. So thank you, Daniel. Appreciate your presentation.